Okay, so a very good morning. So we are going to have the last class of this Bayesian classification as a first class here. Last class we were discussing about doing the parameter estimation is what we were discussing there, and in that what was the estimation technique we were looking in the previous class? Right, maximum likelihood is what we were studying earlier. Now in this class we will study maximum a posteriori probability estimation is what we are going to study. Maximum a posteriori probability estimation. So this we, as you all know, we refer to this as MAP estimation. This is what we are going to study in this class. Okay. So what is it that we need to estimate? What is the parameter name we are using to refer to those parameters, set of parameters? Theta, correct? So it is the theta that we need to estimate here. If you look at the maximum likelihood estimate, what is happening there is we just treat it as a parameter, and then we were doing all estimations that you have some samples of your, you may call it as a process or whatever. You had samples x1, x2, x3, so on, xn bar, right? Each one being a vector. Then we had x, which is nothing but you could think of this x as a matrix or set of all these feature vectors. And earlier, the problem we were looking at is to find out probability of, in case of ML, what is it that we were computing? Probability of theta given x bar or x bar given theta. Estimation, parameter estimation. Yes, you need to find out theta there, correct? So probability of theta given capital X. That is what you are trying to find out there in the ML estimate. We do not at that point of time treat theta itself as a random variable. Notice that these are the n number of samples we are taking for each class. They can be different. These n samples can be different. You may pick up for a different set of n samples, you will get a different result. So there, while you are dealing with the maximum likelihood estimate, that hasn't been done. So we were treating it, we were right away, you see all possible values of theta that will maximize this. So we were, so this probability to get maximized, and we figure out that this can have some kind of distribution here where you are varying the theta here. What was your x-axis here? Probability of theta given x bar. Since you know the x bar, all values, you know a given set of things, you are varying theta, and then you are seeing where this gets maximized, right? How are you getting this probability of theta given x bar? Can you tell me the expression? Right. So you have k varying from 1 to n, correct? And probability of xk given theta, correct? So you have, we again assumed there, each of them are independent, and then you have the summation. Are we right away computing it or doing something else on top of it? We are doing something else. We are not directly computing this. What was that we were doing there? A discriminant function, correct? You are taking a logarithm of it, because why logarithm? You assume there these distributions to be Gaussian. You have 1 over some constant there, and exponential is there. You will get that out. And anyway, your problem is a maximization problem. and it is a monotonically increasing function. So if this function is maximum, natural logarithm of this will also be maximum, and that is easily tractable, right? That's why you are taking logarithm of it, right? Now adds one more layer of sophistication here when it comes to map estimate, maximum a posteriori probability estimate. The next level of complexity added here is theta is not just a parameter. Theta also is a random variable in itself, right? Because for varying values of samples, it can have a distribution. Consider a case where you have a knowledge of what is the distribution to expect. So that should be incorporated there. That's the prior knowledge. If you have it, we should be able to incorporate that prior knowledge. So here you could say theta is considered as a random variable here, right? So now what you will do, you all well aware of this Bayes theorem. Probability of x given theta times multiplied with probability of theta is equal to probability of theta given x into probability of x. Now that's when this is the case now, because you are treating theta also as a random variable, and now it has also a probability density function here, right? Now what is it that we need to maximize here out of all those 4 terms that you see? Probability of x bar given theta. This is what we need to maximize now. Okay, that's what we will attempt now. So what we need to do is probability of x given theta. So how can we write that now? Probability of x given theta is equal to probability of theta given x into probability of x divided by probability of theta. Correct? Now you find out a theta ml. Let me, this is not ml, earlier one we should call it as an ml. Now this is a map estimate. So this I would write it as theta cap map. The map estimate I would get here is that argument, right, that maximizes this for varying values of theta. Now the same thing would now apply here. Now I need to find out, this will be argument. You find out the argument theta that maximizes this one. So, well, what is the term that I could ignore here among these terms? I made a mistake. See, what is it that I need to find out? It's not p of x comma theta. Okay, to check how it is coming, I have written the other way, not paying attention there. This should be this one I should find out. Is that clear? Because you have been given a set of observations, samples. Now you find out theta such that the probability of this theta given those samples is maximized. Hope it is fine. Okay, good. So all I would do here is probability of theta given x, I would write here. This is probability of x. Now this is probability of x given theta, and this is probability of theta. Okay, I'll just erase this part. Right. So now this turns out to be argument that maximizes this one. So what is the term that I could ignore here or doesn't have a role to play in this maximization problem? This probability of x, right? The drawing samples. It's the theta that you are going to find out. So that's equivalent to now probability of x given theta into probability of theta. This is what will give me the map estimate for theta. So you could notice here you have this additional term of p of theta coming here when you compare this expression with what? ML estimate, right? Okay, now similar to what we did in case of ML, we again let's take a logarithm of it. Okay, so before that, let me just write the expression for p of x given theta. How can I write it? Again, you could assume that these are independent observations, are independent, right? So I have n samples here. So pi k varying from n1 to n, probability of xi bar given theta. Okay, so whenever I am writing capital letters here, including theta, this could be a matrix. So for a vector, I am explicitly writing a bar there with a small letter. Okay, to the extent possible, this is the notation that we are following. Okay, now with that here, so this also now you can use this discriminatory function here, and then what will happen? You have argument that maximizes theta. Now you are taking natural logarithm of this whole thing. Okay, natural logarithm of pi of k equal to 1 to n, probability of xi bar given theta into p of theta. Okay, this anyway, this k is anyway, sorry, I should write here xk bar here into p of theta. And of course, then if I take this here, just plus natural logarithm of p of theta, when you compare this expression with the maximum likelihood, this is the additional expression that you are getting there. And this summation would turn out, this multiplication would turn out to be a summation there. Right now, well, how do you maximize this now? This, let's call this as, yeah, this is the expression that you have it here, but how do you maximize this? So let us call with this as with some name. Okay, or yeah, what is the way to find out the maximum value for this expression? Assuming that you have some analytical expressions for p of theta and other stuff, how do you do that? Like first derivative, you take dou by dou theta. Okay, so to find out maximum, so what you could do there is to find out the maximum value. How do you get that? Dou by dou theta of this whole expression, you make it to 0, and whichever theta you are getting as a result of that will give you the value for theta, which is a result of maximum a posteriori probability. Any questions or any doubts so far? So all we are doing is argument that maximizes probability of x given theta into probability of theta. That's essentially what we are doing here. So when you do it, let's call it as whatever you are getting as T map. Okay. Now, when will this give you a result which is similar to the result that you would get in case of a ML estimate? And when will you get a result that is different from an ML estimate? Is the question clear? I can compute, I can estimate these parameters based on the method that we discussed earlier, right? In the previous class. That will give you, let's say, theta cap ML, I will call that. When do I get these results similar? When do I get a very different results from these two? Very good. P theta is uniformly varying. So question is, when will be the results from this will be very close to the results that you will get with maximum likelihood? That's the question. So one thing is, when your theta is varying uniformly over your period of interest, or it is almost same, then you will get the same. Then what would happen? This p theta is when it is uniform, you have the same constant value. Okay, The only mistake in the earlier answer was it is not 1. It just depends on, because then it's no more a PDF, but still you can say it's a constant value, right? So it is in that context, you will get these two results same. Hope that point is clear. And assume that you have a Gaussian distribution. Now assume that you have a Gaussian distribution for P of theta, a slightly different perspective. Now assume that this is also more or less centered around this. Also assume that you have a Gaussian distribution. Okay. Now for these two results to be very similar, if not exactly same, what is the nature of variance that you would expect for P of theta? Should it be high? Should it be low? What should happen? Should it be 0? Why? Correct. That's right. So your variance. So when you look at the Gaussian curve, when the variance is very high, that kinds of flattens out, is it not? A small variance is very much concentrated around its mean. On the other hand, when you have something which is flattened out, that means its variance is high. So if it is a Gaussian distribution, if you assume that this P of theta has a Gaussian distribution, when this Gaussian distribution has a high variance, you would expect these two results to be very similar. So maybe let's draw something to see how it could look like. Let us first draw P of x given theta. Assume that I have a distribution like this for P of x given theta. Now for the other one, you assume that I have a distribution like this. Okay, let's consider that this is my P of x given theta, and consider this as P of theta. Now, what can you comment about the closeness of the results that you would obtain with map estimate versus maximum likelihood estimate? Will they be very similar or very different? Right? They will be very different. You could see here, by the time this is hitting the peak, this P of theta, it is telling you that the probability of having a theta value around this range is very less. That is what this curve is telling you. The prior probability, you have a prior knowledge. This is telling you that, well, you have a very minimal chances of having a theta here. On the other hand, based on the samples, if you are analyzing, this is telling you that this has a very high chances, which they both are not matching. So, well, all you could need to do is, this is a simple multiplication, right? You do a multiplication of these two curves, have it, and in that maximum will tell you what the map estimate would give you. On the contrary, somewhere around here, your theta ML estimate will come somewhere here, because it doesn't look into the prior probabilities. Is that point clear? Why they both give a different result? See, there could be instances, for example, let me take an example from medical imaging, where if you have a CT scan, right, in that, and if you are looking for a particular, let's say there is a tumor, the tumor, you know what is the range of intensities that you could expect for a tumor. So there you have an a priori knowledge of what could be the mean intensity that you could expect there, and around which it varies. You do an analysis over multiple images. From there you would get, assuming a Gaussian distribution, you could get mean and variance values for it. And now assume that you got an image which is affected heavily by noise. The samples are affected very much by noise. Then it is possible you might end up with this probability of x bar given theta, because this is not looking at our prior knowledge about what to expect in the intensity range. So that is one instance or one example that we could cook here, where your ML estimate and map estimates could give you different results. Is that clear? Or any question here? Okay. Yes. Which one? Why they are different? See, this is telling us it is not looking at any of your samples. You know from the ground truth, okay, that you expect that this what could be these parameters. For example, these parameters, theta is, for instance, if you consider a Gaussian distribution, this is the mean intensity and variance in that intensity. These are the theta values. Okay. Now, how did you get P of x given theta? This is purely based upon the samples that you have got, the random samples and samples that you have picked up. But this could be the prior information that you have, right? So when you look at the maximum likelihood estimate, that is completely based upon just the samples. You do not, when you do not have any prior knowledge, of course, that's the best thing to go for. But in case if you have some prior knowledge about what to expect for theta, that is what is incorporated here. This gets simply multiplied here. I can pose it in a slightly different way. Assume that you have no idea about the distribution to be expected for the parameters. Then what will you do? You assume the P of theta to be uniform, because you don't know anything. You give equal chances for everything. So then this turns out to be a maximum likelihood estimate. If you have some idea, that turns out to be the map estimate. Is that clear? Good. Maybe for the sake of completion, I will draw another graph also here, which shows you where map estimate and ML estimates could be similar. Let's say this is my, I'm again assuming that still I have Gaussian. See, as I mentioned, all we were discussing is parametric estimation. So that means your curve can be parameterized by a set of parameters. Okay, just knowing it need not necessarily be a Gaussian. It could be, as I mentioned, various distributions it can take. Okay, for the sake of simplicity, and which is also most common, I am just drawing here Gaussian. Okay, so this you consider now as your P of x given theta, and in this region, this is the kind of what I am getting for P of theta. You could see here, even after multiplication and then finding out the maximum, you would end up with same result almost, because this is kind of more or less constant. Okay, I could have even drawn it with little more uniform than what this is. Okay, then you could clearly notice here, this gives you a case where your theta map is very close to your theta ML, where here they are pretty different here. Okay, hope the concept for a maximum a posteriori probability estimate of parameters is clear. Yes. Not necessary. It is not at all necessary. So I could have drawn it in a different way also. Okay, if you want, maybe I may be having here. It could go something like this also. Still, the you just think of these two corresponding values getting multiplied and getting a new graph there. Okay, so that's not no way that is a constraint that you should have it. Okay, good. So if this is clear, let's work out one example now. Your theta has a value mu. Mu can be a vector or a scalar. Can this be a vector? Yes. If your feature vectors, you have multiple features you are considering, mu bar. Okay, and at this point we are considering, we know the sigma value already. Okay, so there are two terms again here. What are the terms? P of theta, P of theta given x. These are the two terms we have. So suppose for this again, let us assume that P of theta is Gaussian distributed. So what all values should I have for a Gaussian distribution? So let us first look for P of theta. This can be characterized by, let's call this as mu naught. Okay, the mean value for this distribution is mu naught, and maybe sigma square mu. Let me use the same as in an example. Let me call it as, I hope, yeah, sigma mu or sigma mu square. This is the variance. So this is the prior knowledge I have. This is not something that I need to estimate. What is it that I need to estimate here? What should I estimate here? Right. It is P of this distribution is what I need to estimate. Now again, so these are all known here. Okay. And again, this could be a vector, correct? So I'll keep here mu naught bar. To keep things simple, I would consider here a diagonal matrix with all its diagonal elements the same. Okay, then I simply put here sigma mu square here. So P of x bar comma theta. And now I'm considering here is, I know the variance value, because that's one example. If you, of course, in practice you don't know any of these two parameters, you do it interchangeably. You start with some variance, you compute mean, and the next step you take that mean and compute variance, and so on and so forth. Okay, for our case we will consider what is known here is sigma square. This is known. Okay, here also I'm making the assumption that this is a diagonal matrix. What would be the size of this diagonal matrix? L by L, L being the number of feature vectors, and all values across the diagonal have a value of sigma square. Please make a note, these two need not be same. The variance that you are expecting for your prior knowledge about the theta need not be same, but still I am assuming that it is diagonal, so sigma mu I am saying it. Okay, I am nowhere assuming that these two distributions are same. Now what else is there? Let's call it as mu bar, and maybe from our estimate is map, maximum a posteriori probability. So I'll call it as mu bar map. This is something that is to be computed. Right? Would you like to give it a try to compute this? Now I have given you this. Can you give it a try to compute the expression now on what would be the expression for the mu bar? If you are computing it, those of you who computed this, let me call it as mu L bar. Does anyone by any chance remember the expression that you would be arriving at? 1 over n? Yeah. K equal to 1 to n xk bar. Correct? This is what you will be getting for ML estimate. Hope you have worked it out earlier. That was given as a homework assignment or homework problem for you. Now you do the same now for map estimate. Try it out. Argument, okay, that maximizes your theta. Then you could have here logarithm of probabilities of theta given x into probabilities of theta, probabilities of x bar given theta. Correct? X given theta. Correct? Is that fine? Good. So this is what I should find out. Well, this also would become argument that maximizes theta logarithm of probability of x given theta plus logarithm of probability of theta. Is it not? It's just a logarithm. So log of a times b is log a plus log b. Okay. Yeah, I'm writing log, but you assume this is log to the base e, not log to the base 10. Okay. Some of you, while computing your answers, were using log to the base 10. Unfortunately, that is not the case. This is log to the base e, because we have exponential there. We want to get rid of that. That is why we introduced the logarithm here. Okay. So to find out the ML estimate, map estimate, what I should do, dou by dou theta of this whole expression, I should make it to 0. Then whatever theta I would get would give me the map estimate, is it not? So let me call this as some term T1 of theta and this as T2 of theta. So let's solve for each of them. And then finally, let us make it equal to 0. What is your theta there, by the way? Mu, right? Keep that in mind. Okay, don't keep it as still as a stranger. You already know about that guy. That is mu. Is it just mu, or I could write, to be more precise, dou by dou mu bar? Hope you all remember the gradients we computed. So in fact, that's again a vector where you do, for example, you have x1, x2, x3. You compute this derivative with respect to x1, mu1, mu2, mu3 correspond to the mean values for x1, x2, x3. So it's a vector there essentially. Okay. So that vector is essentially, so let me do it for P of, let me write it as mu bar here, for example. This means if I write it, it means actually, I'm writing it as T there, I think. Okay, T1, term 1. Okay. That actually means dou T1 of dou T1 by dou, what should I write? Mu1, dou T1 of mu bar only, let me write it. Dou T1 of mu bar by dou mu2 and so on. How many terms I have here? L terms I have. Hope this clarity is there. Okay. We are dealing with vectors here and its derivatives. So don't get messed up here. Hope keep this thing very clear. Right. I'll erase this out. So let's compute this first. Okay. So let us, for that, and let me write the expression first for P of x given theta. Tell me the expression now. Assume it is an L dimensional feature vector. Now tell me the expression. 1 over, what should I get here? 2 pi times, what is the power here? L by 2, because square root of 2 pi is there, that I have not written square root here. L by 2, and determinant of my covariance matrix, sigma square, and then exponential of minus 1 by 2 into, and here notice here the normal expression is x bar minus mu bar whole transpose sigma inverse x bar minus mu bar. Correct? This is what I would be writing. What is this expression? Sigma square times I. Correct? For the diagonal matrix with equal diagonal elements. So then I could take this scalar out, and what do I get here? Can I write simply as x bar minus mu bar norm square, right? That's all it is. Hope you are all able to again think of it as a vector where I have a1, a2, a3. That is, assume that this is my vector. Consider this, right? So maybe x bar minus, so when I do it, let's consider a1, a2, a3. Transpose, you need to multiply it. So here a1, a2, a3, that will give you a1 square plus a2 square plus a3 square. You look at in terms of norm of this. Norm of this vector is nothing but square root of a1 square plus a2 square plus a3 square. That will give you norm of a, and you are simply taking square of it. Hope the notations you are comfortable with whatever I am writing, right? I use the same here, and now you tell me what do I get here in the numerator for this? P of x comma theta. I told you that it is sigma square there. Now you tell me what do I get here? Sigma square times. So I have x bar minus, should I use, let us call it as mu bar here, and the result is mu map. That is what you are going to find out now. Okay, for the time being I still call it as mu bar here, and norm of it, the sigma square, will I get it then? This one in this manner, is it? Okay, good. So this is the expression you arrived at. Take the derivative of it. See, earlier if you recollect the problem we solved, there two sigma squares are there, we were using a chain rule there. Now don't forget that we are further, this is again, I should write here a small correction. This is xk here, right? This is xk bar, because each one probability you would be computing there. So this I should write it as xk bar there. Hope that distinction is clear. You cannot compute for the whole thing. This is for each sample you have it. Right. Now take a look at there. Probability of your x given theta is nothing but, now you do k varying 1 to n, this probability of xk bar given theta. That is what will give me this. And of course I am consider here natural logarithm here. I put that also here. Now to compute that, look at the expression there. Okay, that is where I am arriving at slowly. So that would give me summation k equal to 1 to n natural logarithm of probability of xk bar given theta. Okay, well, I could write instead of theta, what should I write there? Mu bar I can write, right? Let me not keep this as an alien. Let me put there mu bar. That's what I am computing there. And essentially I need to find out a derivative of it, correct? So maybe before that, let me finish writing this expression here. Well, this will be natural logarithm. What will I get there here? For example, inside the summation, I would get natural logarithm of 1 over 2 pi times L by 2. Pay attention and correct if it is not sigma square. For now I am writing it as sigma square plus, what do I get here? Or let me write minus here, minus 1 by 2 into, okay, xk bar minus mu bar whole square. I still hope that I'll be getting sigma square there. If not, please correct that. So this is the expression you would be getting, for which you need to find out a derivative with respect to mu bar, right? What will be the derivative of this with respect to mu bar? Right, this is 0 when you compute the derivative. So derivative with respect to mu bar for this is 0. All you are left with is this derivative. Okay, and similarly, so this is the only term remaining here for you when you are taking derivative. So essentially you have to take the derivative of t1 of theta plus derivative of t2 of theta, and that you need to make it to 0. So I'm just, for the sake of simplicity, I started with just this term and taking derivative here. Okay, so now let me write that derivative of t1 of mu bar by with respect to mu bar. Okay, so what do I get there? Minus 1 by 2 into, any idea on what will be the derivative of this? Okay, I still hope, again, please correct if that is not sigma square is what you are getting there. Then tell me what would be the derivative of that? 2 times. What next? Xk bar minus mu bar. Anything else? Right. What else do you get? -1. Correct. Good. Because you are taking derivative with respect to mu bar there. Okay. If this is not clear, always when this, see, we are doing derivatives and all on vectors. So if at any point of time it's not clear to you, take a very simple example. Okay. Just a 2-dimensional vector, you take it and see what is going to happen, and then finally come back here and do the reverse engineering. That will help you. Right. So all I am left with here is this will be equal to Xk bar minus mu bar, right, whole into 1 by sigma square. Yeah, very good. I messed it up somewhere. The summation is there here. So the summation is here, correct? So that will give me k equal to 1 to n and Xk bar minus mu bar divided by sigma square. Okay. So in the interest of time, next class is also going to start you in 5 more or 10 more minutes. So you please do the same thing now for the term 2. Okay. And after that, you take these 2 terms, very simple, means once you are able to do this, that is almost a straightforward or a subset of this complex setting. So after that, you sum them both there. Anyway, you can see that you will not get a negative sign there, other than, yeah, anyways, I will not. Yeah, you just look at it. It will be very simple. You do it, and maybe in the next class, I will quickly talk about the result there. Okay. So please continue it and do it by the time you come for Wednesday's class. Okay. And then finally, also make an interpretation now in terms of sigma square and sigma mu square there. So what happens if your sigma mu square is very high? What is your mu maximum a posterior probability value when sigma square is high versus your sigma square is a small value? Okay, you just look at the final expression and see ideally what should happen when the sigma square is very high. You should get the same expression as maximum likelihood expression, which you already know, 1 over n times that summation k varying from 1 to n Xk bar. You should be getting the same expression, and you should be getting a different expression. So write your expression also in terms of sigma square, sigma mu square, means you don't need to write explicitly anything. That's what it turns out to be. So please look at that, and finally I'll be making some comments about it in the next class. Okay, hope that is fine. Good. So see you in the next class, and we'll stop here.